going to go through a relatively simple example of using the work energy theorem to infer how large a force is exerted on a baseball to catch it. So some information going into the problem to assume it's a pretty fast pitch, so close to a 90-mile-an-hour fastball, so about 44 meters per second. Mass of the baseball, 145 grams, and assume that in catching the baseball, from the instant that the baseball touches the glove, it is going to have a displacement of just 5 millimeters. So you're not really like pulling your hand back while you're catching it. You're just basically let it depress into the glove a little bit. And we want to see what kind of force results from that. And the tool that we have to use is the work energy theorem. So the work done by this force over that displacement is equal to the change in kinetic energy of the baseball. And change in physics means final minus initial. And you catch the baseball, so its final kinetic energy is 0. So that's easy enough. The work done is minus k initial, minus a half. Mass of the baseball, 0.145 kilograms, and the initial speed was 44 meters per second. So the work done by this force is going to be, that works out to minus 140 joules. Okay, so let's look at this dot product. Put the two vectors tail to tail on our head. There's the force from the mitt on the ball to the right, displacement of the ball as it's being caught to the left. And so this work is also equal to F dot D. So the force dotted into the displacement. That's going to be magnitude of the force, magnitude of the displacement, and then cosine of 180 degrees, because the force and the displacement point in opposite directions, and we know cosine of 180 degrees is -1. So one side of the work energy equation, we have minus 140 joules. On the other side of the work energy equation, we would have minus magnitude of the force, magnitude of the displacement. So minus minus is plus, so we've got a plus, and solve for this force by dividing both sides by the displacement. So the magnitude of the force catching the baseball in only 5 millimeters, 140 joules, and joule is in Newton times a meter, over 5.0 times 10 to the minus 3 meters, gets me a huge force, 2.8 times 10 to the 4th newtons. Ouch, that is gonna hurt. I could make this force smaller and less painful by pulling the mitt back as I'm catching the ball. That would increase the displacement, and that would reduce this force. This force has to do enough work to bring the ball to rest. That's going to be 140 joules of work no matter what, because we know the initial kinetic energy of the ball, final kinetic energy is 0. This right-hand side is fixed. On the left-hand side, I have freedom though. I could do this with a large force and a small displacement, or I could do this with a huge force and a tiny displacement. And this is all the difference in the world between falling on something nice and soft and cushy like a mattress or couch versus falling on a concrete floor. The work done to bring you to rest is the same in both cases. What's different is what's your displacement over the time that you are being brought to rest. If the displacement is small, then the force has got to be big. If you fall on something that compresses, is squishy, is bouncy, then D can be quite large, and mean the force exerted on you can be small.